Black holes, they're just the perfect Hollywood villain, right? And they're also the stuff of our deepest cosmic nightmares. But how much of what we see in the movies is, real? Well, today we're going to separate that movie magic from the absolutely mind-bending science. I mean, that quote just nails it, doesn't it? It's the popular image we all have, these terrifying cosmic monsters just swallowing everything. It's super dramatic for sure. But is that the whole truth? Not even close. As we're about to find out, the reality is so much stranger. Okay, so if you've seen Interstellar, you know exactly what I'm talking about. That incredible climax where Cooper falls into the black hole, Gargantua. He doesn't just survive, he ends up in this five-dimensional library, a tesseract, and starts sending messages to the past. It is an absolutely wild scene. And it brings up the huge question we're digging into today. Could that really happen? Okay, to even begin to answer that, we've got to jump in a time machine ourselves. We need to go way back, way before Hollywood even dreamed this stuff up. Because the whole idea of a black hole, it didn't start in science fiction. It started in the incredible mind of one guy, Albert Einstein. So this journey from a crazy idea on paper to something we could actually see, man, it took a long time. It all kicked off in 1915 with Einstein's theory, but for decades it was just math, a beautiful theory. The name black hole didn't even stick until 1967. And it took over 100 years, right up to 2019, for us to finally snap this picture. Concrete proof that these cosmic giants are 100% real. Okay, and here's something really cool that Interstellar got totally 100% right. It comes straight from Einstein's theory. Gravity doesn't just pull on things. It actually messes with time. It slows it down. They call it gravitational time dilation. Remember that water planet they visit, the one right next to the black hole Gargantua? 1 hour for them was 7 years for everyone else. That's not Hollywood make-believe, people. That's real, honest-to-goodness physics. So how on earth does that work? Well, to help us wrap our heads around it, Einstein gave us this amazing picture. He said, imagine space and time are woven together into one single thing, like a giant stretchy fabric. Now, when you put something massive on it, like a star or a planet, it creates a dip, right? A curve in the fabric. And that curve is what we feel as gravity. It's not some mysterious force pulling you down. It's you literally sliding down a curve in space-time. The bigger the object, the deeper the curve. So, that begs the question, right? How do you make a dent in that fabric so deep that it basically punches a hole right through it? Well, you need to start with a truly enormous star, one way bigger than our sun. For billions of years, it's in this constant battle. The nuclear fusion inside is pushing out, and its own massive gravity is crushing in. But eventually, the fuel runs out. The outward push just stops, and gravity wins. Big time. The star collapses in on itself in this unbelievable explosion called a supernova. And what's left behind is so dense, so heavy, it warps space-time into, you guessed it, a black hole. All right, so we know how they're born, but what do they, look like? The name black hole is kind of misleading, honestly, because the most spectacular stuff is actually all the action happening around them. So let's break it down. Let's look at the real anatomy of a black hole. First off, you got to know that not all black holes are created equal. You've got your stellar black holes. These are the common ones left over from dead stars. Then you have the absolute monsters, the supermassive ones. We're talking millions, sometimes billions of times the mass of our sun, just chilling at the center of galaxies. Gargantua from the movie? Yep, that was one of these beasts. And then there are these theoretical ones, primordial black holes, maybe created in the Big Bang itself. Some could be as tiny as an atom, but still have the mass of a mountain. Wild. So, that bright, glowing ring you see in the pictures, yeah, that's not the black hole. That's called the accretion disk. Think of it like water swirling down a drain, but on a cosmic scale. It's a vortex of gas, dust, and debris, all spinning around the black hole so incredibly fast that the friction heats it up to millions of degrees. It glows so brightly that it's one of the most powerful sources of X-rays in the universe. And you know what's so cool about that first real photo we got? It showed us something amazing. See how one side of the ring is way brighter than the other? That's because that part of the disk is spinning towards us, while the dimmer side is spinning away. It's basically the Doppler effect, just with light instead of sound. Like when an ambulance siren sounds higher as it comes at you? Same idea. And just from that one simple detail, we can tell which way the black hole is spinning. How cool is that? Okay, get even closer and things get even weirder. You hit a region called the photon sphere. Here, gravity is so intense that light itself, photons, gets trapped in orbit, circling the black hole like a tiny planet. Now, get this. If you could somehow hover right there, light from the back of your head could whip all the way around the black hole and come back to hit you in the eyes. You could literally see the back of your own head. I mean, come on. And then we reach it. The most famous and infamous part of a black hole, the event horizon. This is the line in the sand, the ultimate boundary. Once anything crosses this line, a ship, a planet, even a beam of light, it's game over. It can never, ever get back out. The gravitational pull becomes, for all intents and purposes, infinite. It is truly the point of no return. Which, of course, brings us right back to where we started. In Interstellar, Cooper sails right past the event horizon and ends up in another dimension. So, what would really happen if you took that final plunge? Let's imagine it. You've survived the blazing heat of the accretion disk. You've witnessed the mind-bending photosphere. And now, you've crossed the event horizon. You're past the point of no return. What happens now? And this, my friends, is where Hollywood and hard science take two very, very different paths. Interstellar gives us this beautiful, awe-inspiring tesseract, where time is a physical place you can move through. But according to Einstein, all the stuff that made the black hole, all that star matter, is crushed down into a single point at the very center with infinite density, a point called the singularity. And what about your trip to that singularity? Well, unfortunately, it's not a magical journey through space-time. The gravity at your feet would be so much stronger than the gravity at your head that it would stretch you. It would stretch you until you were torn apart into a stream of atoms. The scientific term for this is, and I'm not making this up, spaghettification. Sounds almost funny, right? But the reality would be, well, a very quick and very final end. Okay, so if they're not gateways to other dimensions, then what are black holes for? What's their deal? Well, now it's time to bust one of the biggest myths out there and really understand their true and, frankly, much more important role in the universe. Right, so everyone thinks of them as these giant cosmic vacuum cleaners, just sucking up everything in sight. But the reality is, nope. A black hole's gravity is just like any other object with the same amount of mass. Seriously, if our sun magically turned into a black hole at the same mass right now, Earth would be totally fine. We just keep orbiting it like nothing happened. You have to get really, really close to fall in past that point of no return. And get this, they're not even rare. Scientists figure there could be anywhere from 10 million to a billion of these stellar black holes just in our Milky Way galaxy. A billion! They aren't some weird cosmic oddity. They're a normal, fundamental part of how our galaxy works. And this might be the most important takeaway of all. Far from being cosmic wrecking balls, supermassive black holes are more like cosmic architects. Our entire Milky Way galaxy is spinning around a supermassive black hole at its center, one named Sagittarius A star. They are the gravitational anchors that literally hold galaxies together. So they don't just destroy worlds, they actually create the stable conditions that allow worlds like ours to exist in the first place. So while we probably won't find a five-dimensional library inside a black hole, we're left with a question that might be even more mind-bending. At the singularity, space-time is supposed to curve infinitely. And according to relativity, that means time itself should stop. It just freezes. So here's a final thought to chew on. If time stops for anything falling in, does that mean from its perspective, the entire future of our universe outside has already played out in an instant? It's an idea that just shows you, the more we learn, the more we realize just how much we still don't know.